Yo, what's up, everyone? Welcome back. Week 7, problem set 2. And we're covering the sampling distribution again this lesson. And the good news here is that what we're mostly going to do is just review the last lesson, which was definitely really important and really tricky. Okay. So everything looks pretty much the same. You probably could do a lot of this already, but we're going to look at it with a particular definition in mind, an important theorem. We don't have a lot of theorems in AP statistics, but we're going to talk about something called the central limit theorem. So I think it's not going to be the longest worksheet. And remember that March is a big month for us. We're going to learn pretty much all the big concepts before our next break. And they're all concepts I really like. Okay. I think the end of the year really ties everything together quite nicely, right? We start with data, we start with stuff like this. Then we get sidetracked with probability, but then we return. So hopefully you're strapped in and we're getting there. First, I just took this graph from online. For one reason, because like when you see data in the real world, it's probably going to be set up not just in like a Google Sheet chart or something like that. But what this says is that the following graph shows the average income in the US by household in 2010. The mean is 50,000 and the standard deviation is 8,000. So this is a very common set of given information, the mean and the standard deviation. And we know that they both relate to the z-score if a distribution is normal, okay? And this is gonna get tricky, so I really appreciate you for leaning in. But what I'm looking at first is not a normal distribution, right? And we should be very clear about that. This is the distribution of wealth in America by household, right? And if I asked you to describe the shape, this part's a little funky. It's basically saying like 9% of the country is really, really rich. But other than that, we're skewed right? So this is what the distribution looks like if I was to just do a simple sketch. And it's not normally distributed, okay? So if I asked you to do like what percent of data is above 60,000 or above 70,000, something like that, you couldn't use the normal distribution, okay? Because this isn't the normal distribution. You could look to find, and I know it's so like you'll have it printed or whatever, but you can't see 60 from your perspective right now. But you could find what data was above that just by kind of counting up the boxes. But this distribution is not normal. Okay. Okay. So this is confusing. Lean into that. But here's the big idea. If you were to take a random sample, that random sample is going to look pretty similar to the truth, right? So if I were to survey 100 Americans or 500 Americans, it's probably going to look like this shape, right? And then the bigger that sample is, the more it looks like the initial shape. However, once you start taking samples and once you start making a distribution of samples, that's when the distribution starts to become normal, okay? And I recognize that that's really, really confusing. So again, you can think of just collecting data as taking a bunch of individual samples, right? Or a bunch of people as a sample of one. I think this is not going super well, but that's okay. For A, it says sketch what the sampling distribution will look like for samples of 5 and calculate the standard deviation of the sampling distribution. So think that this is what happens if you have samples of 1, right? You're just collecting data. But let's talk about what happens if you collect random samples of 5. So think, just like last time when we were circling random numbers, if you were to randomly select people, most of those people are probably going to be over here, right? They're probably going to be less than the mean because we're skewed to the right. So if you were to kind of randomly take a sample in this kind of distribution, think that you'll get a lot of answers that are probably close to the center, but you're likely, if you take a random sample of 5, to have at least one data point push you towards the right, okay? So a random sample of 5 might have something that looks like this. And if this is my numbers and I add them up, I'm going to get a value, in this case, that's actually too big. But I'm going to get a value that's closer to the center than most of my data. Okay, so think that as your sample size gets bigger, you're more and more likely to get skewed by the big points. And that means that most of your samples aren't actually going to be like their average isn't going to be where the distribution is, but closer towards the center. Okay, so random samples of 5 are likely by at least one of those 5 points to be skewed, right? An individual sample doesn't have many, but think that a bunch of averages are going to start becoming higher because it's more likely that you get one of those skewed values. And again, all of this isn't too essential. We're learning the most complicated topic in statistics, the central limit theorem, but I hope that makes sense. So if you take a bunch of samples of 5, it's not going to be completely normal yet. It's going to be close or like kind of in between normal and skewed to the right, where a lot of my samples might still be under 50,000 in cases where all 5 of the random people were also under 50,000, right? So it's going to be skewed. Let me do it this way. It's going to be skewed right, but it's probably going to be less skewed right than last time, okay? If you take a random sample of 30, think that it's almost guaranteed that that average is really close to the true average, okay? If you have a sample of 5, you might be over or under, depending on how many of these points you would get. But if you have a sample of 30, think that it's going to be pretty realistic and it's going to be pretty close to the center, okay? So that's the big gist of this. I don't know if I explained it perfectly. The second example should tie things up more. Crap. But think that we are getting closer and closer to a normal distribution centered around the average or 50,000. Once the sample is big enough, right? So what we're going to talk about is that 30 is considered the minimum sample size for a valid sample. Once we get past that, we can assume the distribution is going to be normal, but it's going to get more and more condensed, okay? And just think that the reason it's going to get more and more condensed is the standard deviation of the sampling distribution. So I'm not going to make you sketch any of them anymore, but what I want you to think is that we have a mean in the standard deviation of the entire population, but the sampling distribution, we'd have to calculate that new standard deviation, okay? And that just tells us how varying the samples would be, right? And the bigger the sample size, the closer all of the samples are going to be to the average. I really hope that makes sense because I think we're getting there. I think it's all starting to come together. A sample of 100 Americans is going to get really close to the average, right? You're probably going to be equally represented everywhere. So almost all of your samples are going to be close to that. Samples of 30 are going to be pretty accurate too, right? But they're not going to be as accurate. So the difference would be kind of the lines on the bottom, right? So let's just calculate 2 standard deviations here. You start with standard deviation given, and then you take the square root of the sample size. Again, always think what are formulas accomplishing? And what this is accomplishing is it's saying that all the data is going to be closer to the center. So 4.1 divided by standard deviation is that. Compared to that, right? This means that everything is much more condensed. Every standard deviation away from the center is not half, but almost half as it would be here. The standard deviation in this case would be even bigger, and the distribution isn't normal, okay? This one would be 1.83. So again, standard deviation measures spread. So that's all that. I hope that makes sense. And if you listen through the whole thing, I think it's pretty logical. But here we're going to talk about some definitions. I decided I would just give you the definitions for this. And it says, what is the central limit theorem? And what are the conditions that need to be met for it to be true? And the central limit theorem is that the sampling distribution is normally distributed so long as the sample size is large enough. Okay, so let me write that first. So long as we're taking large enough samples, we can assume that all possible samples are normally distributed. And then what we're going to start doing towards the end of the year is making sure that we list the conditions, right? Because all the math that we're doing from now on rides on certain things being true that we've just been kind of building towards. So the first thing that needs to be true is that your samples need to be random, okay? And I know that sounds almost silly and obvious, but if you're taking samples that are inaccurate, think you're doing something that would make more people with higher incomes respond, you're not going to get a normally distributed sampling distribution. So when it says conditions, the first condition that happens the rest of the year pretty much is that the sample is random. And again, that's just like last week. It means that you're doing a sampling method that is unbiased. So for the distribution to be normally distributed, the sample has to be random and the sample size has to be greater than 30. Okay, that's going to be our working definition right now of a large enough sample size. Think that those small samples have more room for error. 30 isn't even perfect. You're still going to get some variation in the possible samples, but 30 is what we consider the minimum. Okay, so right now the central limit theorem is that the sampling distribution is normal as long as the sample is random and the sample size is greater than 30. Okay, cool. I hope that went well. And the second part of this, we're going to just get technical and review using the normal distribution to answer these questions. So this is a much more likely AP kind of style question. We'll go through it, but I think we crushed it. So it says the average ladybug has 8.5 spots with a standard deviation of 3 spots. Part A says, imagine you take a sample of 300 ladybugs and find that the average has 8.1 spots. What is the z-score for this sample? So with all of that we talked about with the sampling distribution, the whole point of it is to compare a sample that we take with the truth, okay? So this is the truth. Think that they've researched ladybugs forever, and the average ladybug is 8.5 spots. We want to see how likely is this sample, this 8.1, if this is true, right? We're just comparing the truth to our sample, okay? And the scheme of a sampling distribution, this is a large sample, and you don't need to draw it on your own for your own problems. But we know that the average sample should be 8.5, but we got a sample of 8.1. Okay, so it's asking for the z-score of the sample within the sampling distribution. All that means is we need to find the standard deviation and use the z-score formula, right? So the standard deviation for any sampling distribution takes the given standard deviation, which is 3, and divides by the square root of sample size. So solving for the standard deviation is going to be a pretty common thing for the rest of the year. And I'm getting 0.173. Okay, that gives us context. Just by eyeballing, that looks like 8.1 is around 2 standard deviations below the center, which is a pretty rare outcome. But if we want to find that z-score, all I'd have to do is take the sample, that is my data point, right? This is what I did when I did my study, minus the mean divided by the standard deviation. So 8.1 minus 8.5 divided by 0.173. So the whole point of finding a z-score is to find percents and above and below that z-score. So what B says is if 8.5 is true, the population mean is true, what percent of samples would have an average below this sample? Okay, So what you're really trying to figure out is how uncommon or how rare is this sample going to be if the population mean is true. Think that we're assuming this has to be the center. But if that's the center, we want to know how likely is this outcome or something even more extreme. Okay, so we already have the z-score, and all I have to do is plug z into the z-score formula, or sorry, no, z into the table, and it's going to tell me the percent below. Negative 2.31. So 0.0104. Or 10.4%. I hope that makes sense. And what that means in the context of this is that only 10% of samples, if you take 300 ladybugs, would have less than 8.1 spots. Okay. And what I want to acknowledge is this is kind of weird, right? This isn't particularly useful yet, but this concept is going to be really useful when we don't know the truth. Okay, so that's kind of what we're building towards. We're pretty much done. For part B, all I want to do is go the other way with the z-score chart because last time I forgot. So it says, imagine you take a random sample of 300 ladybugs, but have yet to find the average. So we don't know the average, but it's saying that 90% of samples will have a mean that is greater than what value. And I always like to sketch any normal distribution kind of question. And it's saying 90% of them are going to have a mean that's greater than whatever we found here. Okay, so we're trying to find this value. We know the center is 8.5. And we're given the percent above, right? 90% of the data is above this point. So if we want to use a z-score formula, never forget that you can only plug in the percent below, right? So if 90% of samples are greater, that corresponds with a z-score where 10% is lower. So we'll go to point as close as we can get to 10. Oh, also, and then, damn, last time I did this wrong. That's so funny. I was just trying to write it in my head, but it was actually just 1% last time. I was trying to remember the number in my head and I couldn't remember it. But yeah, this time we find the percent that's closest to 10%, and then we go and find the z-score from there, which is negative 1.28. Once you have the z-score, we can now find what the sample data point is going to be by leaving that as x in my equation. And at this point, we're pretty much done. I kind of just skipped through the math, but the formula always stays the same. Multiply this over this way. That number plus this is going to give us x. So 90% of samples are going to have a mean greater than 8.3. B says a sample in the 5th percentile will have an average of how many spots? And think that the 5th percentile just means that only 5% of people are less than you, and then 95% are above. So percentile questions are really simple because all you have to do is find that percentile on the chart, right? So whatever would be closest to 2, that'd be like the 2nd percentile. Whatever's closest to 7 would be the 7th percentile. But we're trying to find the 5th percentile. And we're estimating a lot. Both of these are equally far away. And if you choose either one, that's fine. So I'll just choose negative 1.64. And once I have that, I do the exact same thing I did last time. So hopefully you're seeing how useful and how simple the z-score formula is. And let me just speed through the answer again. Really similar answer here to the last one, but that's fine. So a sample of 8.2 is in the 5th percentile. Very quickly, let's just do this. I wrote it, we should do it. If the sample has a mean of 9, what percent of samples will be greater? 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean greater than 8.3. 9% of samples will have a mean gre So here we're starting with the data point. We're going to convert the data point to the z-score and then find percent below from z-score. 9 minus 8.5, 0.5 minus 0.173. Z equals 2.89. And then I look for that on the chart. 2.89. And I'm getting 0.9981. Final thing, we should say this so that you don't make the most common mistake. And after you put something in the z-score formula, find the percent below, it is really tempting to be like happy and think you're finished. But you do always have to be concerned if it's talking about greater than or less than that point. So it's saying what percent of samples are going to be greater than 9. But 9 is all the way over here, right? So not a high percent of them are going to be above it. 99% are not going to be above it, but 1 minus that. So again, the z-score chart tells you percent below. If you want to find percent above, which is based on what the question asks, you just have to do 1 minus that. So that would be our answer, 0.19%. All right, we crushed it. I hope the logic stuff wasn't too bad for you. But next week we move on to some great stuff. And I think this was a great week too. I appreciate you.